Okay, so today we'll do two things. So last time we talked about functions and procedures, right? Do you guys all feel comfortable with using for loops in Vhcl? Not for synthesizable designs, right? But for debug, right? So if we wanted to write for loops to test an adder that has 4 bits, right? So if you wanted to test all possible combinations of a 4-bit adder, you would need 2 carry-in states, right? 0 or 1 for carry-in, and then 2 to the 4 for each of the inputs. So that would be 16 iterations of A, 16 iterations of B, and 2 iterations of carry-in. That's what 2 times 16 times 16 inputs, which you wouldn't want to write out that many lines by hand. So in general, you would want to write something like for all of CNs, for the A's, for the B's, right? It's 3 for loops embedded in each other, where the last one has a weight in it, so that you're not there for just one delta, right? This way we can step through, get results we want. Everybody's happy instead of having to copy and paste 1,000 lines. So there are useful tools that we have for debug, and I've shown you some of them, right? So our first debug step is always simulation. And we want to be thorough with this testing. One example that I have for my 2700 course students, a lot of them designed, well, they designed a full adder and then turned that full adder into a 4-bit adder. And many of them didn't test their carry in. So they just set carry in to 0 and ran their test and it worked. Then they built the 4-bit adder and expected it to work, but didn't because their carry in wasn't behaving correctly. That's what I mean by test thoroughly. So if you think you've tested thoroughly, you can end up in a problem situation because you will build some fundamental block and then use that down the line. And now the big one has an issue. And you're like, oh, but I tested the little one, so it's got to be at the high level. So for ones like this, don't forget that you can do an assert statement that checks for the addition to be correct, right? Where this is just saying that whatever sum is equal to A plus B plus Cn, whatever those happen to be. And that will return, if it returns true, everything's good. If it's false, it will report whatever error it tells you to, right? With using the report command. So that's the first step in the debug. The next step is, we all know, I think very well by this point, that just because it's simulated correctly, or apparently correctly, doesn't mean it's going to work on the board, right? And some of this has to do with some things that we can write in code aren't synthesizable. The big one is like counters, right? Where you think you've initialized the counter in simulation, it works, doesn't work in implementation. So one way for debugging is something that I've had in the code previously and something that I use frequently, which I call the status lights. So these are lights that light up when, depending on like what state you're in, or you might have like sequential lights that build up as it steps through some process, right? You can use these output lights to update where your board is and just look at it. If we're having issues, right, in simulation, does anyone in this class, so I had actually a couple of my night class that weren't aware yet of how to access internal signals in the simulation?
Open that that side menu and drag them in?
Yeah, yeah. Does anyone not know that the internal signals are? You don't? Okay, I'll show that. So there's this issue where when you launch a simulation, it by default shows you the top level signals. Let's say your SPI is not a top level signal and you want to know what the state is. The bad way to do it, and this is what I learned was taught by a previous professor, is to create an additional port that then you can look at those signals. That's not a good way to do it. Instead, in Vhcl, we can access internal signals of these modules by clicking on the side tab that is listed as scope. Then there's a side tab called objects, and then you can browse through the hierarchy and find what these internal signals are and just drag them into your waveform and see what's going on inside. If you're debugging, right, the first things that I always recommend dragging into that waveform is your state, because that's the most important thing. What state is having an issue. And then the second one is the counters. Whatever it is that's keeping you in that state for a fixed amount of time. And then any signals that are pertinent to changing states. So if you're waiting for some condition to be true to leave a state, add that signal. Because that's where most of your bugs are going to be, is in state transitions. After we have that, I will pull this up and show it on the overhead for anyone that doesn't know, but I think most do. But the next thing is going to be brand new. So I talked about the I2c Lab last time, right? And it's going to be complicated, to say the least. I've started looking at it, and I think you're going to need upwards of 9, 10, or 11 states. This can be really tricky to debug if it doesn't work on the board. So there is a tool that we can use called a Debug Core. So a Debug Core is a tool that Vhcl provides for us that is a soft core, so it's a little processor, so it takes up a fair chunk of room on your FPGA. Not really an issue for us. We have tons of room on our FPGA compared to what our design is doing. The soft core allows you to have what we call probes. Probes are like when you take an oscilloscope and measure one point versus another, right? But these are digital probes. And then they can send data back to Vhcl, and you can actually view the signals on your FPGA in real time. And I will show you how to do that today. So I have to make sure this setup is going to work. And for Zoom, I have to switch to screen sharing. Go to the bottom. Okay, so good. Right, we're all familiar with Vhcl at this point. I've loaded up a project from a student that is just your SPI completed project. And let's just go, I'll start with the simulation, right? Hopefully this won't take too long. Oh, there we go. So this simulation window, don't worry, I don't have it quite set up correctly yet. Right, we're used to seeing this simulation window. If you want to access internal signals, for those couple of you that don't know, on the side here, you can click on scope, and that pops out this hierarchical list of what goes on in your project, and then objects, which list any of the nets inside of these modules. So if I want to look at the inside of this SPI master, right? So that's not the top. this brings up the full list of nets inside the SPI master, and I can go find the state. I've already dragged it in this example, but all you do is click, drag, and you have a new signal. That's how you access internal signals. Very important. So let's say we've done the simulation, and we feel confident in our simulation, but something's not working on our board. So we would run all the way up until synthesis, including synthesis, and then you open it up and you'll notice that it says this right here on the side where it says setup debug. All you have to do is click that. Now what's nice in this Vivado is it will create the debug cores for you, which used to be a really obnoxious process, but you don't need it. So I'm just going to say continue debugging. Actually, maybe I'll remove them all and show you guys from the beginning since I've already done this. Okay, so starting from nothing. This wizard is going to help us set up debug is what it says. So this says we can add nets that we want to debug. So looking forward, and even at the SPI, one of our big challenges is what's happening with the memory, right? That's a big thing to simulate. It's a lot of signals to look at, and it's one of something that you might be not familiar with. So let's say we want to debug what's happening with the memory. Well, let's come over into here and say in the top net list, I want to go and find address. So I want to make sure that I'm writing the correct address to my memory. I then also want to say, well, what is data out doing with that address? And lastly, I might say something like, well, I also may need to come into my SPI master and I might, inside of the SPI master, really care about what this countdown is doing. Okay, so now I've got 61 signals that I have probes attached to. I just click next. Okay, sample data depth. Now, the FPGA runs way faster than we could interpret as a human, right? So even if we could look at all those probes in real time, they'd just be flashing past and be no meaning to us. What this does is every time I tell it to take a sample, it will store some number of samples that I can look at. So 1024 is the default, so it's going to just take a snapshot in time with 1024 signals. I can turn that up or not. These, I won't go into what the advanced options are, but I'm going to turn them on for the moment just so I can use them. Then I just click next, click finish, and it's going to set up our debug cores. Now, unfortunately for everyone, you then have to run implementation and so after that, so that would be after you do that after running synthesis, set up debug, run implementation, and then generate your bit stream and program your device. I'm going to see if I can get away. Zoom and make sure I don't break anything with the Zoom people. I need to make sure that, okay, microphone's working, everything still appears to be working for Zoom. So now I can plug in the FPGA. I'm going to see if I can get away without running implementation because I have a very slow computer for this. And also adding the debug cores adds a lot of time to your implementation. What's that?
We'll just run it on Brock's computer.
Oh, does he have a nice one? Okay, so I should already have a debug core set up inside of this that will have different signals. Okay, so once I run it, this is the window that's going to come up. If you end up losing track of this window, which can happen really easily, and this took me way too long to figure out, in order to get back to that window, you just click on Program and Debug on the left side, and it will come back. Okay, so now that I have the debug window, let's do something useful with it. I'll start from scratch. So what I can do is I can hit this run trigger for this ILA core. So ILA core is what we're talking about, the debug core. Something to know about these debug cores is it's difficult and maybe impossible, I haven't checked yet, to make them work across what we call clock domains. So we've only been working with one clock domain. We have 100 megahertz clock. But you might build an FPGA system where part of the FPGA is at 100 megahertz, part of it's at 400, and part of it's at 20, and maybe some of it's like 20 kilohertz, right? You might have different speeds, and the debug cores want to know which clock domain they're in. For this, the case of this is really easy. There's one clock domain, you're not going to screw it up. Just be aware that going into the future, these debug cores get more complicated. And something I haven't figured out yet that is much easier with Altera, which is the Cordis, Altera and Cordis, right? Major competitor to Xilinx, is looking inside of the memories. I haven't figured that out yet, which could be useful when we get into the I2c Lab when we're supposed to be storing stuff into RAM. I don't have a way to do that yet, but this is a useful way to look at signals. So let's say I hit run. It's just going to pick that moment in time. It's going to send a command to the FPGA to send me back these signals. So we're looking at the SPI master's data in, the address, and the countdown. Right? And so we can see here where countdown is pausing for lengths of time. I know that this happens inside of idle. So I know what state I'm in there. I could even add state as an output to help debug. Probably a pretty good idea. But I just want to demonstrate. But this right now is essentially random, right? I have no control over when this is going to stop. So what I want to do then is create what are called triggers. What is the condition for it to stop? To do that, I come down into the trigger window here. Be careful about closing this one. It took me a hilarious amount of time to come back and find where this trigger window is, and I don't even remember where it ended up. So try not to close the trigger window because it's really frustrating to get back. So if I want to add a trigger and say, let's trigger it on address. So a common bug that I've seen in the memory is that you've run through the sine wave and then it drops to 0 for some amount of time, and then the sine wave starts again instead of being a continuous sine wave. So the reason this happens is usually that you're reading memory addresses that are out of bounds for what you've saved into it. So you saved 100,000 samples and you're trying to measure addresses from 100,000 to 131,000. That's going to give you bad outputs. But let's say we suspect this is true, but looking at our code, we don't see that that's happening, and we want to go check that. Well, we pull up address. And now we can say, have an operator of, I want to trigger when address is equal to, not equal to, etc. But let's go with equal to, because transitions are what's important. And I could say something like, well, let's go look at the address when it's just zeros. Right? So now when I hit the go button and I run my trigger, it will stop at the moment when address is 0. Right here. So now I can look at what address came right before 0. Right? Ideally, this should be address number 99,999. Again, something you may not know, in simulation and here, you can right-click on the signal of interest, go down to radix, and you can change it to what representation you would like. So hex is the default, but you can go and say, I want it to be represented in binary or octal or ASCII.
ASCII is always the weird one because it's not compatible if it has the wrong number of bits. If you're in what's the word I'm looking for? Simulator. I think the simulator has a few more radix options than the Debug Core does. So this is showing that my debug, this one is running at 100,000 and then going back to 0. So this is working with the addresses. Or not. It looks actually to me like it's running one address too long. Minor hiccup, probably not even going to be noticed, actually. I don't know how else you would find this out other than using the Debug Core, in fact, because it's such a tiny little blip in the waveform.
That was a thing I had where every so often you had a little spike.
Yeah. So you can also create ANDed operations where you can create multiple conditions for when that trigger should go. But that's going to be a little bit more advanced and we'll walk through. And you can even come in here and set up some other trigger modes. Okay, do we have any questions on debug cores? Okay, I suspect you're going to find this very helpful when it comes to the I2c Lab. It's going to be a hard one. We're not adding anything new. I will iterate that again, other than the in-out pin and writing to memory instead of just reading from it. Those are the two new concepts. The big thing about this is it's now a big state machine, right? Lots of states. I strongly encourage you to, no matter how you design the SPI interface, to use the two-state method for both read and write. So the two-state method is where the states control the clock. So you're going to have a state where the clock is set up and the data is set up, and then a state where the it's all clocked in. So it looks like this device is rising edge triggered, whereas the SPI one was falling edge. So setting up the clock involves setting it low. So you'll set the clock low, set up the data that you want to clock in, and then raise it high. You're definitely going to want to start out by drawing a state diagram. If you don't draw a good state diagram, you're going to have a really hard time writing the code. And then you can always check off with me to make sure your state diagram is going to work, and I can point out where issues are.
So one question, with the in-out, do you, when you're going to read from it, do you set it to like the out to like PC?
I believe, I have to double check that you're just going, you can just assign it to it, and the synthesis will take care of what the output needs to do. So you'll just switch which side of the equation that the input or output goes on, and the synthesis will take care of it. As long as you don't try and read and write in the same case statement, or sorry, inside the same case within a whole case statement, right? But we won't, because we're gonna have a transmit and receive states, which are gonna do different things. It should take care of that for us. If not, we'll figure it out.
Because I basically remember something with the speed for it has, but
yeah, I don't think you have to set it to Z. I think it will be okay, but we'll check it, because this is new for me, because, and I'm pretty sure I said this in the last time, I almost never use I2c because of the added complexity. SPI is faster and simpler. It just costs wires, which can be a design decision that actually really does limit you, but I try and avoid it. So, other questions? We'll get to I2c right on, today, right? Who isn't going to be, like, who hasn't finished the SPI? A couple of you, okay. I recommend finishing that soon. I know it's a lot of work. I've gone a little bit light on the homework assignment so you guys can stay up. That doesn't mean you spend less time on the class, that means you spend the time on the labs, because if you fall too far behind on these labs, it's gonna get miserable at the end. A lot of the meat of this class is in the labs. They're very important and will apply directly to you getting a job. That I promise. But as though you don't have enough to worry about, we are going to have an exam on Monday. So now I will talk a little bit about what's going to go on to that exam. And I will probably post at least a couple of review questions so that you get some practice working at that. So let me.
Look like you're still on screen share. People watching.
Oh, that's okay. I will switch that back. Thanks for pointing that out.
I think they can still see the.
Well, yes, but they can see this camera
Yeah.
because I have to unplug that camera in order to use the FPGA. But we'll get them switched back. Thanks for pointing that out.
He would have been very disappointed, and I would have had to make a new video. And you wouldn't grade their homework. I'm very proud of myself. I got a whole lot of homework grading done yesterday. So I'm getting caught up.
Just in time to grade that other test.
Yeah. Okay, looks like mic's working, everything's working. All right, so, exam, right. So, just a topic overview for what's going to cover. This starts way back with the lecture where we talked about PALs and PLAs. So I can ask you to do something like well, there's multiple ways to do it. Let's do it the one way, right? Where I color a bubble. Right? And then ask you, so it could be this way and ask you what function is implemented here. Or it could give you a function, say, implemented in PLA or PAL logic. And I might ask you, what's the difference between a PAL and a PLA? Little things like that. This exam will be open note, open book, open internet. Just do not ask other people for help. So do not post questions on, what is it, Stack Overflow, or Chegg, or any of those various other homework ones. If you get caught doing that, you will fail the exam and probably fail the class as a result. And if it's not your first time, you'll get kicked out of the department, which is not fun. So don't cheat. Cheating is just asking other people. Every other resource is okay. So COVID is blowing up, especially down in Salt Lake and South. We are lagging behind a little bit on that. We don't have that many cases on campus yet, but I don't want anybody to be in a position that they're worried about what's going to happen to the exam if they fall ill. So the way it's going to work is you can take this exam anywhere. I'm just going to open it up at the beginning of class, and it's going to close 15 minutes after class. Those 15 minutes after, well, maybe it'll be 10. I'll let you know for sure. But it's those time after isn't more time for the exam. That's to make sure you get it submitted, right? So I will give you at least 10 minutes to get it submitted and making sure that it's submitted correctly. So make sure to take advantage of those 10 minutes rather than trying to cram through a few more answers and then not getting any points because you didn't make the submission window. What this means is you can take it anywhere. I don't care. You can come to class. I will be here in class and I will be on Zoom to answer questions. It's going to last only the duration of class. I will try and make it less time cramped than the previous one. I'm still learning with that. But you, wherever you are, you will need access to Vhcl. Now, you may have to run synthesis I will not ask you to program a board. So things that I could do with Vhcl are, I might give you code and ask you to say, write a test bench to identify the problem with it. This could be like an adder or a multiplier or a spy device or something else. And you're going to have to write a test bench and test it to see what the problem is. I might also create an issue that doesn't look like it has any errors in it, but when you try and synthesize the design, it pops up with errors. So you're going to have to run for synthesis and then use the TCL messages window in the log to identify and fix whatever that problem is, right? So debugging issues in code. So similar to the first exam where I asked you to hunt down what is wrong with this VHDL, but that was all syntax. This time I am very likely to ask you questions, what's wrong with this VHDL, but it's going to be like Vhcl errors, or it's going to be conceptual, right? It's going to be like initialization of counters or errors that happen when you transition between states. So I could give you like a spy device, a spy master interface with a problem in it and ask you to find it. I might also give you a waveform of, say, a multiplier and say, this is a waveform of a multiplier. Why is the output not correct? And you would need to debug that with just essentially a simple diagram and the output waveform. So it's showing that you can read test bench waveforms. You had a question? You can copy and paste. So yeah, it's going to be digitally available, and copy and paste. It might require a little bit of reformatting when you paste it in, but yeah.
So it's like not going to be on paper, like it sounds like.
Well, it's going to be a combination of the two. Where you're going to, so the question, most of it, I will try and make it so you can just do it on paper. And so the question will be, what is wrong? Like, describe what is wrong with the code, where is the error, and what would you do to fix it? Right? I'm probably not going to ask you to submit, well, I won't say that, because maybe I will ask you to submit some VHDL, which is probably better off typed than handwritten. So you may want to get comfortable taking code and just copying and pasting it into Word and then turning that into a PDF. So I'll let you submit multiple files in this, but I want them as PDFs when you submit them, which is part of the 10-minute submission window I'll give you to make sure that you have time to finish the exam and get a clean submitted file so I can grade it. As it gets closer to the exam, I will hopefully send out an email that has anything else you need to know so that there's no horrible surprises. So there will likely be questions about adders and multipliers. Probably won't ask you to program a multiplier, but questions about it are relevant. There will be questions about drawing state machine charts and diagrams, right? So know the difference. You'll have your book, so it's not like you can't look it up. But remember, diagrams are the circles and charts are the ones with the squares and the decision boxes, right? That's a chart element. Know what the chart element means and how to transition from them. Know the basic ideas of microcode, right? What are the requirements for it to be microcode? And then I might ask you, given this state diagram, turn it into a state machine chart that is compatible with microcode. I won't ask you to create the microcode circuit, but I might ask you questions about the microcode that uses a ROM, right, from that lecture, where it's going to be something like a ROM, a buffer, a mux, right, because we have to output some sort of test.
And based on the test, we can choose. So this would be next state, and this is current state, right? And then it might have outputs Z going out. And I might give you a chart like this, right? That says, given address 0, so here I have addresses, and if I'm in 0, I'm in state 0. Fill out the rest of the table to accomplish X, right? So it might be, here's a state diagram, fill out the table that implements the state diagram, or the state chart, or whatever it is. Remembering that this next state is microcode. One of the main thing that you're looking for is it can only do one test in microcode, right? And microcode test can be more than one bit. You could ask something like, is X equal to 0, 1, 0? Right, that is a valid test. But the decision is either true or false. So like it might be next state true, stay in state 0, next state false, go to state 1. Right? And then what are the outputs doing when I'm in each of these states? Remembering that we will stick to more state machines for microcode, because it's difficult to get the output logic correct for Mealy. Possible, but it adds complexity and it's no longer truly microcode. So then you have to ask, what is the test? What are we testing if true? So we just write something like, well, you can do it a couple of ways. You could just write x1 and then off to the side you write x1 is, right, something like that, asking what the test is. And then you just fill out this table. Also, right, microcode, again, only makes one decision. If I give you a state diagram, state 0 is happily microcode compatible because it only has to decide 0 or 1 to go to the next state. But let's say state 2 has this decision matrix. Right? It could go to any one of those states. Now I have, well, if X is equal to 0, if X is equal to 1, or Y is equal to 1, and this would be like if, and you have some specification, I have to define it, right? Where it's like, well, 1, 0, or 1, 1. So Y would overtake X's or something, right? I have to define my outputs and priorities. The general idea is if it has 3 arrows coming out of it, it's not microcode compatible. So I might give you a diagram and say, turn this into a state machine chart with the appropriate number of states such that it is microcode compatible. I might ask you questions about FPGA resources, not to like implement them, but like, what is an IP core? I might ask you questions about benefits of using built-in multipliers. I might ask you questions, what happens if you use all of the multipliers and need another one? It might be block memory versus distributed memory. As I mentioned, I might ask you to write a test bench that might use it. I might ask you to write a procedure for it, or I might ask you to write for loops to test all cases, right? I can ask you for a test bench in order to test something. I might ask you questions about synthesizable versus non-synthesizable code.
I might ask you questions about the SPI protocol and its implementation, right? So we've had that lab. We're supposed to be done with that lab, so all of the questions about SPI are fair game. I might also ask a question like, here is a data sheet for a device, a SPI device. Write a state diagram, draw me a state diagram to control this device. That's the bulk of what will be on the exam. As I said, I will post at least a couple example questions. It won't be like an example exam, so it's not going to be like a complete, but it'll be some of the questions that I feel you might not have had enough practice at in the homeworks, so that you don't get to the exam and feel completely befuddled. I did hijack a sample exam from Dr. Brown, so I have a pretty good idea of how to write one of the appropriate length. We'll see how that goes. Just this one. I don't think you'd like this one.
It's Dr. Brown's. I've had him before.
Yeah, but it's a little bit of an older one.
Probably.
But I don't know. I mean, some of the questions are pretty good. I mean, this one gives you a state diagram and it says draw an equivalent SM chart for this state diagram, testing only one input and do not add additional states. So like it's not unusual. Then he did on this exam actually a very similar thing to what I did, but his is, where is it? He gave you a, on this one, a whole page of code, similar to what I did, and said this purports to be a 4-bit shift and add multiplier that has errors in it. Identify the errors. You lose points for identifying errors that aren't correct. I didn't do that to you guys, right? I left off that last bit. Guess wrong didn't count against you, but so it's actually not, it's not too bad, and mine shouldn't be too bad, I hope. The Vhcl parts might be the most challenging, but they're also the most important. I want to make sure that you guys understand finding and identifying errors using the TCL console. Questions?
How would you turn that into microcode?
You just have to add 2 states, or add 1 additional state. So your first test would be it. So if I'm assuming that if y is 1, I go back to 0 regardless of what x is doing. Let's make, like, I would specify that, right? So let me redraw those numbers so that that's clear.
Or you just put like y.
So using the format x comma y, it would be 0, 0, 0, 1, and 1 don't care, right? So then I would just need, the first thing that matters in this case is y. If I don't care what x is when y, my first test is y true? And then I go to another state that evaluates if x is true or not. So just add a state. Yeah.
What if y is not?
If y, well, so if y is true, go back to state 0. If y is not true, go to a state that evaluates x. Yeah. So it's just a matter of adding states so that I only make one decision at a time.
Okay, I guess I was just, when I tried to think through it, I was like, you can't like do that and have the same amount of like clock stuff.
Correct.
Right?
Yeah.
So,
Yeah. Your state machine gets slower whenever you add states. So, and the terminology, I might ask you a question about that, is I would be increasing the critical path, right? If there is questions about a procedure or anything like that, because it's fresh material, it would be simple. Next exam might have a more complex procedure question, but if I do any procedure or function-oriented questions, they'll be pretty simple. We haven't had like homeworks or implementations of those yet, so it will be conceptual mostly. Other questions? Okay, you guys are all experts, and that makes me happy. I'm going to end early. I will hang out and help out with any code that you guys need. So I am doing this on purpose, just so you guys know that ending early, because I know many of you have a hard time making it to office hours. So I like to be here in a time that you can be here to help with code. Because as I said, the lab is probably the most important part of this class as far as your futures go. Use it as a chance to either finish up SPY or start looking into that I2c and drawing out like the state diagram to puzzle out how you're going to approach this I2c state machine. We've got tons of time. The other class actually took a lot longer. They had way more questions than some of the other stuff, but I think it may just because this is the second time I've given this, so I got better at the lecturing part, so there's less questions. And I had way more issues with the debug, to be honest. This went a lot smoother. So I guess if you end up watching this on Zoom and you're not here, that's probably not going to be very interesting from here on out, but so I'll stop recording. If you're watching Zoom, feel free to send me emails or office hours, which you can schedule via Zoom if you can't make it in, because I know COVID is going around.